Hello, hello, hello. Welcome back. Second recording in a day for the advent of cyber. But the good thing is that I finally caught up on all the missing challenges. So the shellcode, the GRC, the phishing, it's on one of the lives. I think it was like 2 hours and 30 minutes. I solved all of them there. It was pretty interesting. So now we are ready for day 22. It's because I'm cubed, isn't it? Huh. Kubernetes, DFIR. What is IR? I know what is, I have an idea, but don't let me go for it. Mayor Mauer laughed hard at what he had done. Another scheme hatched, another seized scheme won. But a thought passed the mayor. The thought then passed twice. The list soon to come, the town's naughty or nice. He paced and he paced like the week of election until that was it, a surprise mayor inspection. The list making wares, well, it only seemed fair. Who'll grant him temp access and account for the mayor. The list makers agreed. Under certain conditions, he logged on that day to confirm his suspicions. The next day they were when the naughty list read Mayor Malware, line 1, he read it with dread. The condition they gave, there was something they missed. Somehow and some way he accessed the list. Mayor Malware's then smiled. As he had find no blame. With this, he will find a new home for his name. Oh my gosh, that was horrible rendition, but that's fine. Learning objective. Learn about Kubernetes, what it is and why it's used. Learn about DFIR and the challenges. Digital forensic. Thank you. I knew the IR part, but I couldn't recall the first part. Digital forensic in incident response and the challenges that come with DFIR in an ephemeral environment. Learn about DFIR, how DFIR can be done in a Kubernetes environment using logs analysis. I think I'm just tired, right? Doing 7 challenges in one day, it's insane. And talking for that long, I'm probably just tired. So what are we starting today? We need a VM. We don't need the attack box. And there's split screen. This is probably my favorite type of doing these challenges. Kubernetes explained. Back in the day, it was very common for companies / organization to use a monolithic architecture when building their applications. A monolithic architecture is an application built as a single unit, a single code base, and usually a single executable deployed as a single component. For many companies, this worked and still does to this day. However, for some companies, this style of architecture was causing problems, especially when it came to scaling. The problem with monolithic application is that if one single part of the application needs scaling, the whole application has to be scaled with it. It will make far more sense for company with application that receive fluctuating levels of demands across their parts to break the application down component by component and run them as their own microservices. That way, if one microservice starts to receive an increase in demands, it can be scaled up rather than the entire application. The great microservice adoption. Microservice architectures was adopted by companies like Netflix, which is a perfect example of the hypothetical company discussed above. Their needs to scale up services dedicated to streaming when a new title is released, billing and blah, 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 made a microservice architecture a no-brainer. As time went by, companies similar to Netflix hoped aboard the microservices express, and it became very widely adopted. Now, as for the hosting of these microservices, containers were chosen due to their lightweight nature. Only, as you can imagine, an application of this scale can require hundreds, even thousands of containers. Suddenly, a tool was needed to organize and manage these containers. Introducing Kubernetes. Well, you guessed it. That's exactly what Kubernetes was made for. Kubernetes is a container orchestration system. Imagine one of those microservices mentioned earlier is running in a container, and suddenly there is an increase in traffic. And this one container can no longer handle all requests. The solution to the problem is to have another container spun up for this microservice and balance the traffic between the two. Kubernetes take care of this solution for you, orchestrating those containers when needed. That makes things a lot easier for everyone involved. And it's because of this, along with the widespread adoption of microservices architecture, that Kubernetes is so ubiquitous in the digital landscape today. This popularity means that it's highly portable, as no matter what technology stack is being used, it's very likely a Kubernetes integration available. It's very likely a Kubernetes integration is available. This, along with the fact it can help make an application highly available and scalable, makes Kubernetes a no-brainer. In Kubernetes, containers run in pods. These pods run on nodes, and a collection of nodes makes up a Kubernetes cluster. It is within a cluster that Max Kitty and co-host investigation will occur today. If you're interested in learning more about Kubernetes, we have a range of rooms on the subject. A good place to start will be the Introduction to Kubernetes room. Then there is plenty more where that came from with the Kubernetes hardening module. Okay, so Kubernetes containers runs in pods. These pods run in row nodes, and a collection of nodes is a Kubernetes cluster. Okay. DFIR basics. Every cybersecurity professional has stumbled or will stumble upon DFIR at some point in their career. It's an acronym in IT. We all love our acronyms. That stands for Digital Forensics and Incident Responses. These two investigative branches of cybersecurity come into play during a cybersecurity incident. A DFIR expert will likely be called to action as soon as an incident is ascertained, and will be expected to perform action that fall into one or both of the two disciplines. Digital forensics, like any other forensics disciplines, aims to collect and analyze digital evidences of an incident. The artifacts collected from the affected systems are used to trace the chain of attack and uncover all facts that ultimately led to the incident. DFIR experts sometimes use the term post-mortem to indicate that their analysis starts after the incident has occurred and is performed on already compromised systems and networks. Incident response, while still relying on data analysis to investigate the incident, focuses on responsive actions such as threat containment and system recovery. The incident responder will isolate infected machines, use the data collected during the analysis to identify the hole in the infrastructure's security and close it, and then recover the affected systems to a clean, previous to compromised state. Pure incident responder, as an emergency first responder whose aim is to contain the damage, extinguish the fire, and find and stabilize all the victims. On the other hand, the digital forensic analyst is a crime scene investigator or detective trying to recreate the crime scene and ultimately find evidence to identify and frame the criminal. Both roles are expected to document all findings thoroughly. The incident responder will present them to explain how the incident happened and what we can learn from it. ultimately proposing changes to improve the security stance of the entity affected by the incident. The digital forensic analyst will use the findings to demonstrate the attacker's actions and eventually testify against them in court. In the task at hand, we will help Max Kitty and the glitch become digital forensic analysts and retrace the malicious actor's steps. We will especially focus on collecting evidence and artifacts to uncover the perpetrator and present our analysis to Wareville townspeople. Okay. Excruciatingly ephemeral. Oh, that's hard to say. DFIR can be a lot of fun. It's easy to feel like a digital detective analyzing the crime scene and connecting the dots to create a narrative strings of events explaining what happened. What if the crime scene vanished into thin air moments after the crime was committed? That is a problem we face regularly when carrying out DFIR in a Kubernetes environment. This is because, as mentioned, Kubernetes workload run in container. It is very common that a container will have a very short lifespan, either spun up to run a job quickly or to handle increased load, etc., before being spun back down again. In fact, in this year, 2024, Cloud Native Security and Usage Report, SysDig, found that 70% of containers live less than 5 minutes. Wow. So what can we do about it? Well, not to worry. It just means we have to expand our digital detective toolkit. The key to keeping track of the ongoing is in your often ephemeral workload within your Kubernetes environment is increasing visibility. There are a few ways we can do this. One way is by enabling Kubernetes audit logging, a function that Kubernetes provide along for requests to the API to be captured at various stages. For example, if a user make a request to delete a pod, this request can be captured, and while the pod will be deleted and logs contained within it lost, the request made to delete will be persisted in the audit logs. What requests/events are captured can be defined with an audit policy. We can use these audit logs to answer questions which help us in a security/DFIR context, such as what happened, when did it happen, who initiated it, to what did it happen, where was it observed, where was it initiated, to where was it going. Of course, this just scratches the surface in terms of level of visibility we can achieve in our Kubernetes environment. We can feed audit logs as well as event from other security relevant sources into runtime security tools, which help transform these raw events into actionable data, which can then be visualized using yet more tools. A digital detective should invest in an extra large toolkit. If you want to learn more on that subject, check out the Kubernetes Runtime Security Room. Following the cookie crumbs, let's start our investigation. Finally, what is that? 13 minutes in. As mentioned before, some of the log source will disappear as their sources like pods are ephemeral. Let's see this in action first. On the VM, open a terminal and start a Kubernetes using the following command. So we are minikube start, right? Starting. Minikube. Okay. Using the Docker driver based on existing profile, starting control plane, new node, minikube in cluster minikube, pulling base image, restarting existing Docker container for minikube. This container is having trouble accessing the registry. The pull new external, you may need to configure proxy. Okay. It will take roughly 3 minutes for the cluster to configure itself. You can verify the cluster is up and running using the following command. Okay, we're going to wait for it to configure itself. And once it does it, we are going to Let me just open the second terminal here. So we got that. It's going to be kubectl, which is the command line tool for Kubernetes. If I'm not mistaken, get pods -n whereville. Whereville. It's probably not ready yet. So I'm just gonna, if all the pods are up and running based on their status, you're ready to go. This will take another 2 minutes. Since we know that the web application was compromised, let's connect to that pod and see if we can recover any logs. Okay, so now we can do this. Error? Wow, why? Why am I getting errors? I'm not supposed to be getting error. Since we know the web application was compromised, let's connect to that pod and see if we can recover any log. Connect to the pod using the following command. So just one moment here. What am I supposed? It's not configured to use Minikube cluster and default namespace by default. Okay. So we clear that. And then when we come up here, why aren't you showing me? Yes, okay. Wow, running. Cool. We have all of them ready. Great. If all of the pods are up and running, yeah, 2 minutes. All right. kubectl, kubectl, execute, dash, what is the name? Namespace, I'm assuming, whereville. What is this? Naughty, or nice, -it. -- we are launching bash. So we're connecting. Okay, what did I miss? Okay, it's not right there. You are actually in separated. So we are naughty or nice is the name of the pod that I assume we are connected to. Okay. Once we are connected, let's review the Apache log. So we're gonna cat /var/log. Okay, /log/ are we looking for something specific? Apache 2 access.log. Because those are usually long. What are we looking for? 127, 172, 172. Get favicon, get. Style CSS. So this is just connecting tailwind index. We're getting API, HTTP. We're getting the root and then style. Okay. And then API.php. We're posting into API.php. What was that? So we got this here. That's kind of interesting. Copy. Oh, no. Okay. API.php, we're getting it. So we probably posted something there and now we're getting it again. Get API.php, get Shelly. Oh, probably a reverse shell. This is usually a syntax of a reverse of a web shell. How about that? Web shell. Because we're running it in here. So we probably posted something in it. Why is it called API.php actually? That's a good question. But hey, don't let me get lost. Sadly, we only see the logs from October 28th. Yes. When our attack occurred later on. Looking at the log, however, we did see something interesting with a request made to a Shelly.php. Yep. File. So this tells us we are on the right track. Terminate your session with the pod using exit. Fortunately, Mike Skiddy knew that the log source was ephemeral and decided to ensure that remote backup of the source were made. Navigate to our backup directory. So we're gonna wait. Okay, never mind. I was already out. CD home. So it should be in here. Where is it? Dir artifact. So we got to move into that. Okay, cd dir DFIR. DFIR. Okay, we change into that where you will find the log store in Pod Apache. Review this log to see what Mayor malware was up to on the site and answer the first 3 questions at the bottom of the task. What would be the best way to read this thing? VI, pod access. Yeah, I feel comfy in VI more than anything else. Let's see. Wow, that's a lot. I think we got that already. Looking at it, Shelly.php. Shelly.php. Okay. What file did the mayor read from the pod? Okay, let's see here. Let's go back. So we get. We don't care about all this get. API.php. Okay, tailwind, API.php. API.php, Shelly. So we got that. Who am I? And then we get that. Assets, okay. We got the logo, options. Okay. Command, who am I? More, command, okay. Go away. Who am I? ls cat db.php. db.php. What tool did Mayor malware search for that could be used to create a remote connection from the pod? db.php. Netcat. Which netcat? So which would tell you where, if the binary exists and where it's located. Usually, sometimes it might not be available, so you need the full path in order to run it. Okay, that's done. Where are we going next? We did that. Sadly, an investigation hits a bit of a brick wall there. Firstly, because the pod was configured using a port forward. We don't see the actual IP that was used to connect to the instance. Also, I see 127, 172. Okay. And we still don't fully understand how the web shell found its way in the pod. However, we rebooted the cluster and the web shell was present, meaning it must live within the actual image of the pod itself. That means we need to investigate the Docker image registry itself. To view the registry container ID, run the following command. Okay. Cute that. So Docker ps. I assume we will have to log into one of them. Let's see here. I think I can clear, right? I can clear Docker ps. So we got registry, privilege, and what's the other one? Now let's connect to the instance to see if there are any logs. So container name. This is going to be interesting. I don't play with this every day. This is a good, it shows you how far behind you might be in whatever it is you're doing. So this is good. I don't play with this every day. It's going to be interesting. So we run Docker ps. Let me copy this and come up here. Boom. Maybe not there. Maybe not there. So container ID, this is the ID. Image using registry 2.7. The command, this is a command created 2 months ago. Status up 19 minutes. This is a port 5000 to port 5000. And okay. And then what the heck is this? Registry priv. Container ID is this one. Why am I seeing this way? That's my question right now. I need better real estate. Sorry. If you're not familiar with something, take a break, take a step back. Take a slow step back and just make sure that you see what you need to see. And for me right now, it means, I need to see it like this. Container ID. This is an image here. Okay, let's see here. Let's do this again. Why is that name down there? Container ID image right there. Name, Minikube, and registry priv. Okay. Command entry point created. All right, that's what I couldn't see. These are my two names. Where are you? Where's the other one? So we got Minikube and we have this one. I'm probably gonna start with registry priv, just because. Is it you? So let's see here. Let me go back to the small screen. Dun 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 dun. Dun 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 dun. What are you pasting? Why am I not surprised? Okay. So we need to copy this. We need to copy you, come back here, paste it there, clear this, paste it, come up here, paste it, unable to start. Permission denied. Okay. Container name. ID. Oh, I need to give ID maybe. Either the container name or the ID, right? Let's see. Okay, that's what it was. It's not intuitive, okay? It's not intuitive. So it's either that. So this is one command here. The other one is, where's the ID? It will be this guy here. So it's either that or this guy here. So we can do this, come back here, clear this, just because I want to confirm that. No. Clear. Did I copy too? Oh, shit. Go back here, paste it there. Come here, just confirm. Paste it there. Yes, okay, good. Again, since we hit a wall, we don't have any registry logs. Luckily, Docker itself will keep logs for us. Let's pull those logs using the following. So, what do I have here? I need Docker. So we're gonna do that, delete that, Control A, Docker logs. All right. What do we have here? Oh, shit. Okay, probably more real estate. I need to see. Shit. Let's run this again. And let's see. What do we have? Can I save that in a file and read it later? Yeah, there's way too many. Now we have something we can use. This log have been pulled out for you. Okay, thank you. Because it was just never going to happen. And so we want to read Docker registry logs. Okay. Oh, we're searching. We're catting. Why did I cut? I don't cut. Oh, no. Okay, that's fine. We are grabbing head and we are cutting at the delimiter is a space. Delimiter is a space, and we are choosing the first field. Okay, let's give us that's a lot of data. Okay, the first field is the IP. All right. But isn't it what we already had in the previous logs? How is that different from this? We already had that 172.17. Let's start by seeing, okay. We got that. which is the IP. We can see that the most two connection to our registry were made from the IP. However, we can see the connection is also made from 10.10.133, which is not an IP known to us. Let's find all the requests made by this IP. So we're also going to run grep. We're not going to grep head. We are going to grep 10.10.130.253. Dun, 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 dun. Yep, we have that. Let me clear just because I need the delimiter right there. Okay, way better. Okay, get v2, manifest, get v2, and then manifest. Okay. What am I looking? This is I don't know this logs. I'm making sense, but git commit. What is it? Okay, let me see what they're saying. But we are getting somewhere. If we review the first few requests, we can see several authentication attempts were made. 401, 200, 401, 200, 200, 401, 200, 401. 401 is what, unauthorized? Yeah, access denied. I think is unauthorized. 200, 200. So when did it change to? Probably after, let's see, 200. When was the last 401? The last 401 is right here. We were getting the V2. Okay. Is returned. Yes. Manifest. What is that? 29 at 1250, 1226. Okay, right there. Is it you? Get V2. Yeah, okay, right there. Got that. Nope, it's not you. This one here. Manifest 200 Docker, blah, 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 blah. Okay, we got that. We also notice the user agent in the request is Docker, meaning this was a request made through the Docker command line interface to pull the image. This is confirmed as received several requests then to download the image. From this, we'll learn several things. The CLI was used to connect to the registry. Connection came from 10. Okay, which is unexpected since we only upload image from 172. The client was authenticated, which allowed the image to be pulled. This means that whoever made the request had access to credentials. If they had access to credential to pull an image, the same credentials might have allowed them to push a new image. We can verify this by narrowing our search to any patch HTTP method. The patch is used to update Docker images in the registry. Sorry. All right. So we are going back to reading the file and we're grepping, and then we're also further grepping it just to select the patch. Let's see here. We only have 2 patches. Uploads. Okay. This is not good, which it means that malware could push new version of our image. This will explain how the web shell made its way into the image. Since malware pulled the image, made malicious updates, and then pushed it to push this compromised image back to the registry. Use the information to answer question 4 to 6 at the bottom of the task. Now that we know the malware had access to the credential of the Docker registry, we need to learn how he could have gained access to them. We use this credential in our Kubernetes cluster to read the image from the register. So let's see what could have happened to disclose them. So question 4 to 6. 4 to 6. What IP to that was unexpected? That would be the 10.10.130.253. What's the name? At what time the first connection made? was made from this IP to the Docker registry. That will be the first one that we search for. What time? What's the format? 29 October. Okay. Plus 000. I'm assuming it's all of this that we need. Copy. Okay, cool. We got that part. How far are we? I don't even know anymore. Grep patch. Okay, we did that. Okay, it looks good. We need to know where they got the credential. So we're gonna clear this. All right. MaxKitty was made aware that malware was given user access to the naughty or nice Kubernetes environment, but was assured that by the DevSecOps team that he wouldn't have sufficient permissions to view secrets, etc. The first thing we should do is to make sure this is a case. To do this, MaxKitty decides to check what role was assigned to the mayor. She first checks the role bindings, bind the role to a user. So we're still on the Kube. So we are Kube CTL, the get role bindings. Come on, role bindings, and the namespace is Wareville. Job runner binding role mayor user. MaxKitty then sees a role binding name after mayor malware and decide to take a closer look. So we're gonna go back to that Kube CTL. Describe for me. Why don't you autocomplete? Role binding mayor dash user dash binding, and the namespace is Wareville. Label none, role name mayor user mayor malware. Okay, from the output we could see that there is a role mayor user that is bound to the user mayor malware. MaxKitty then check this role to see what permission it has, and therefore mayor malware has. So Kube CTL describe role mayor user and the namespace Wareville. So what resources pod he can create, he can get, he can list. He can get list, describe, get list. In the pod he can get, he can list, he can watch. And I don't know about the role bindings, the RBAC stuff. I don't know about them. The output tells something, a lot of permission listed here, as you would expect for a non-admin user. All of those expect the permission associated with pods, execute, create, get, that they can create. Exec allow the user to shell into the container using running within a pod. This gives MaxKitty an idea of what mayor malware might have done. To confirm her suspicions, she checked the audit logs for mayor malware's activity. So I'm gonna clear this. I'm gonna cd to DFIR and cd, well, let's clear first and then cd to DFIR artifact. We are going to cat audit logs. We are going to, this is too long to type. Nah, I'm not gonna do that. It is just too long. Copy. Boom, boom, boom. Not just too long, it also creates. There's a lot of room for mistakes. And I don't want that. Paste it there. Should be in good company. Oh, that's a lot. What are we looking for? What are we looking for? Okay, event. This log snippet tells that mayor malware attempted to get secret stores in the cluster but received 4 or 3 responses as he didn't have sufficient permission to do so. A plural get commands run a list on the backend, and it's why it appears in the logs. User malware. Let me see if I can make sense of this. Kind event API version, requested OD ID, request URL API VON namespace where reveal secrets, limit 200 verb list user, group. Okay. Wanted to access secret. Okay. All right, I see. After being denied, okay, get roles. We need to get roles now. Let's see. We're gonna cut that audit log file again. Clear that. Paste it there. We're gonna come up here and paste. Go away. All right. Is it the same thing that I'm looking at? It should be different. Why do you look the same? Why are you trying to look the same? Nah, they look bigger. These logs here look a little bigger. Kind event, V1 metadata, audit, response, complete. Request URI, authorization, runner, example, source IP, user agent. Yeah, the logs are different, definitely different. Response status, metadata, stage stamp, timestamp, are back, all owed by role binding. Okay. After being denied secret access, malware started snooping to see what roles were present on the cluster. So we are going to run this. Copy. To the tube. I should probably copy one sample output. Because I'm sure they're gonna send me reading that again. Okay, another different set of logs. What is it about? Username, malware, grab caller. What are we looking for? Cat audit logs. Okay, what roles were present? Okay. This just tells me when it was received. It doesn't tell me. So the kind of event, where do you see the resources role? Resources secret? Yeah, I'm not sure. While running the previous get role, have found a role named job runner. This log tells us Mayor Malware then describe this role, which would have given him key piece of information regarding the role. Most importantly, for our investigation, it would have told him this role has secret read access. To get the role bindings, I'm just gonna run all of them. Paste it there. Come on now. Clear, and we're going to paste it again. Okay, our bag allowed. Overall, okay, what are we looking at here? Kind of event, API version. Okay, Kubernetes secret namespace. Kind of event, API version. Kind of event, API version. Okay, secret is forbidden. User malware. Okay, I saw one of those. Response complete. Okay. Systems. I saw authenticated. Resources IP. Man, looking at these logs, you can get blind. This is where automation and filtering, you'll learn all the shortcuts because this is, yeah, it's painful to read. Authorization, response group, annotation, allow by role binding. Okay. Reason all. Okay. At some point he was allowed. He was at first denied and then he was allowed. Now knowing this role can view secrets, may or malware try to find its role binding to see what was using this role. Okay, more cutting, copy. Boom. We're gonna come up here, clear, paste it there. Another clear. We are going to paste it there. Okay. Can we add a line in between? Because this is request URI. What am I looking for here? Secrets group in the API whereville. Reason forbidden. Details. Okay. API group. Okay, allowed by role binding. So at first it's being forbidden and then name job runner. Okay, namespace API group. Okay, I'm not making sense of all the logs yet. It's not fully making sense yet. I'm getting it here and there, but not fully. So let me just go to the next. After seeing a role binding name job, role binding, I saw that too. Malware described it and found that this role is bound to a service account name job, a service account that has permission to view secrets. Copy, clear. We are going to come up here, clear as well, paste it there, go away, come back and paste it. Okay. What are we looking for? API version list username, malware, user agent, Kubernetes, object resource pod, response status, time stage, authorization. Okay. Here we can see the malware now armed with knowledge that a service account has permission he needs to list all pods running in a whereville with a kubectl get command. Copy this, go back there, put it there, clear this, paste, go away, clear, paste it there. Again, way too many things to read. Via response study, metadata, user malware forbidden. Okay, we're gonna go. How important is this gonna be into answering the question? Because I think reading the making sense of the logs require a lot more time than I set myself to have to solve these challenges, and that's why I'm just skimming through. I think that's the correct word. Morality checker. Malware described the pod as a morality checker. He then will have found that this pod run with the job runner as a service account, meaning that if we were able to gain access to this pod, he will be able to gain read access. More logs, reading, copy, clear, paste it there, clear. Okay. What am I looking at? That's the problem. The thing is that I need to know what I'm looking at. As mentioned, the role discussion, the permission is usually not included in a non-admin role. It is for this exact reason that this is the case. McSkiddy feels confident that the DevSecOps team had overly permissive role-based access controls in place in the Kubernetes environment, and it was this that allowed mayor malware to run and exec commands as captured by the logs above and gain access into the morality checker. To confirm her suspicion further, McSkitty ran the following command to retrieve the log captured from the job runner service account. Okay. More logs. Paste it there. At this point, I'm not even reading the command anymore. I just want it to be done. Okay, what do we have here? Service account, Wareville. That's what we gave, right? Job runner, service account, authentication, source IPs, 10.244. Oh, this might be interesting. User agent, kubectl. Namespace must be unique. Is required resources automatically. Okay. Name type, format. Okay. This is probably an interesting command to have. I'm just gonna write you somewhere here. No, I don't want that. I need this one here. This one. Where are we? Yes. This is the one I need. Because I see some stuff that I might want to go back to read if there's a question that I need to answer related to that. Oh, I see a B64. What is it? It's config JSON. Okay. Dun. Here we can see a few commands being run. We can see Mayor Malware is able to run the get command on secret list, but most importantly, we can see he has indeed been able to escalate his privileges and gain access to the pull cred secrets using a job runner service account. So we also need this. We are no. We are going to copy you as well. Just paste you here because my instinct of screaming, you might need this. So put it there. This is the one we're looking for, right? Right there. Then now go away. We want to clear this. Paste it. Come up here. Go away. Clear. We want to paste it there. Tun. Isn't it what we just read already? It will look like it. Okay, the final piece of the puzzle resolved around this secret. Finally, she runs the command and the attack path is confirmed. Let me copy this. I was sure something needed to be done with that B64 stuff. Yep. Pull credential and decode. Let's see here. Tudum. How am I doing time-wise? Oh, I have 7 minutes away from the 1 hour mark. Okay. Clear. Let's paste this here. What do we see? Mr. Nice. You're probably going to need you. Copy that. Okay. Shaking her head, McSkitty then confirmed that the Docker registry pull password is the same password as a push password. This means that after retrieving these credentials, Mayor Malware would have been able to make the Docker registry push we saw earlier and ensure his malicious web shell was deployed in the Kubernetes environment and gain persistence. It is for this reason that push and pull credentials should always be different. With that, the investigation is all tied up, the conclusion being that Mayor Malware most certainly belong on the naughty list of the year. Ah. Why? Why wasn't I sure? Well, I was sure. Oh gosh, I was sure. What's the value of the pole secret? So, is it this? Let's see. Is it all of this? Let me check. Okay, we got that part. At what time is the updated? I think I saw that. What command gave it to me? I think if we look right into, let's see here, not you, access.logs. Was it the access? No, it wasn't you. So when did we start grep patch? I think it was, didn't we enter that 1226 already somewhere? 29. Okay. So I am pretty sure that this is a command that will give me the answer that I'm looking for. Paste. Nope. Okay. Cat docker registry logs and grep 10.10.130. I know I saw that somewhere. 253. Ah, not you. I need to grep it. Okay, that's fine. Oh, okay. I know I saw a push here at some point. Wish, blobs, sha. Oh, wait, it's the patch one. Where's the patch? Yes, let me look into that and then grep. Given that the patch is update Docker images. What's the question? Let's make sure we understand the question. Okay, so we got that. At what time? Okay. Upload 12:34:31. Why do I have two patch? One is October 29, 12:34, 12:31. Oh no, 12. Let's see here. Let me copy this. Is one of you? Yes. Cool. Yeah, reading the logs is I could go blind just parsing through all that data. So a lot of respect for the blue teamer. It might be tempting because, well, then you're just correlating and doing some investigation. It's tempting, right? Compared to maybe the red team where you just have to get, like, it could be boring just chasing the right entry point, when with blue team you're correlating, you have all the data, you just need to make sense. So I feel like once you master the art of filtering, regardless of what tool you're using, you should be in a good position. But hey, that was day 22. This is already a personal victory. It has been a victory since the 19th because I've never gone this far. And I'm so happy that today I took the time to catch up on all the challenges that I hadn't completed before. So yeah, we'll see you tomorrow if everything goes well. Until then, take care of yourself. Bye-bye.